Hey everyone, and welcome. Today we are diving deep into a really powerful tool for any Go developer, fuzz testing. We're going to take what looks like a perfectly fine piece of code and just watch as a fuzzer completely tears it apart, only to help us build it back way, way stronger.
You know the feeling, right? You write a new function, you test it with all the usual stuff, and everything just works. But what about all the things you didn't think of? The weird edge cases, the corrupted data, basically the true unknown unknowns that are just waiting to crash your program.
Well, that's exactly where fuzzing comes in. You can think of it like an automated, chaos-loving code tester. Instead of you sitting there thinking up test cases, the fuzzer just generates thousands of random, mutated inputs every single second, and it relentlessly hammers your code looking for weaknesses you had no idea were even there. And we're not talking about small, minor bugs here. Fuzzing is a security powerhouse. It's designed to sniff out some of the most critical vulnerabilities you can imagine. Things like SQL injection or denial of service attacks. These are the kinds of bugs you absolutely want to find before anyone else does. So to see how this all works, we need a little example. Let's take a look at a very simple Go function. All it's supposed to do is reverse a string. And when you first look at it, it seems totally clean, totally logical, and completely correct. The logic itself is really straightforward. It takes a string, turns it into a bunch of bytes, and then just swaps them. It takes the first byte and the last byte and swaps them, then the second and the second to last, and so on until it meets in the middle. Seems like it should work, right? And hey, when we run it with a normal English sentence, it works perfectly. We reverse it again, and boom, we get our original string right back. Looks great, no notes. All right, so being good developers, the next logical step is to write a test to make sure this behavior is locked in. We're going to write a totally standard unit test to prove our function is doing what we think it's doing. So we'll set up a few test cases here. We've got our classic hello world, just a single space, and a string with a few symbols. The key thing here is that we are telling the test exactly what to check. We are only testing for the things we already know about. We run go test and there it is. That beautiful green pass. Now, for a lot of us, this is the moment we'd commit the code, merge the PR, and just move on feeling pretty good about ourselves.
I mean, the code works, the tests are passing, so we're done, right? Yeah? Not even close. It's time to stop being so predictable and to introduce a little bit of chaos into the mix. We're going to turn our simple unit test into a fuzz test and just let the computer do the hard work of finding all the weird stuff for us.
Now, turning a unit test into a fuzz test is actually pretty simple. You rename the function from test to fuzz. The parameter changes from a star_testing.t to a star_testing.f. Our old hand-picked test cases become seed inputs using f.add. And then the real magic happens inside f.fuzz. This is where we tell the fuzzer what should be true for any random input it dreams up.
With our new fuzz test all set up, we run it with just one new flag, fuzz. This tells Go, hey, don't just run the seeds I gave you, start making up your own crazy inputs. So, let's see what happens.
And wow, that was fast. It failed almost instantly. The fuzzer didn't even have to try. It immediately found an input that makes our function spit out an invalid UTF-8 string, something our unit test never would have caught. So what happened? Why did it fail so quickly? That error message is our first big clue. We're not just getting the wrong answer, we are fundamentally breaking the string's encoding. And here is our culprit. The fuzzer fed our function a multi-byte character, like this Chinese character. Since our function was just reversing the raw bytes, it completely scrambled the sequence of bytes that makes up that single character, and the result is just invalid UTF-8 garbage. The fix, it turns out, is pretty straightforward, but it's super important. Instead of reversing bytes, we need to reverse runes. A rune is just Go's way of thinking about an individual character, no matter how many bytes it takes to represent. This change respects those character boundaries and keeps our string valid. Okay. We're using runes now. Our logic is character aware. We fixed the bug, so the coast should be clear. Let's run that fuzzer again, just to be sure. Are you kidding me? It failed again. And this time it's a totally different, much sneakier error. The fuzzer found an input where reversing it twice doesn't give you back the original. How is that even possible?
So this bug is a lot more subtle. It's not about valid characters getting scrambled anymore. It's about what happens when the fuzzer starts feeding our function strings that are already invalid garbage.
Okay, so let's break this down. The fuzzer created a string with a single byte that is not a valid character. When Go sees that and tries to convert it into runes, it basically says, I don't know what this is, and it replaces the bad byte with a special replacement character. So our test fails because the original garbage input and the cleaned up version are no longer identical.
This discovery really pushes us to make our function even tougher. Instead of just letting bad data get silently fixed, the truly professional way to handle this is to detect it and explicitly report an error.
So here's the final, hardened version. Before we do anything, we add a simple check to see if the input string is valid UTF-8. If it's not, we just stop right there and return an error. Then we update our fuzz test to know about this error so it can focus on finding other, more interesting problems.
And now the real moment of truth. We run the fuzzer one last time, but we're not just going to tap it. We're going to let it run for a full 30 seconds, generating hundreds of thousands of inputs, really trying to break it. And the result? A solid pass. We have finally built a truly resilient function. What a journey, huh? We started with code that looked absolutely perfect. The fuzzer shattered that illusion, forcing us to fix a bug with character encoding. We fixed it. And then the fuzzer immediately found an even sneakier issue with invalid data, which led us to our final, truly robust solution.
At the end of the day, this wasn't really about a simple string reversal function. It's about a mindset, and it's about a ridiculously powerful tool. So the real question, the one I want to leave you with, is this. What hidden bugs are lurking in your code, just waiting for a fuzzer to find them?